So I'm honored to be here to introduce our method in CASP-16. So I will thank the CASP organizer and assessor for this opportunity. You can see from my title, we are not doing very simple in CASP-16. We just to try to optimize input sequences to get input predictions. So I will introduce the method pretty later. So I have three parts in my talk. So the first one is to introduce our method. So this is an overall overview of our method. So you can see it's very simple. Basically, we're trying to mimic the real situation when you solve the protein structure. So here, when you get the input sequence, what we do is just generate the multiple sequence alignment. So this pretty special process. We try to predict the disorder region for these sequences because when you solve the protein structure for the experiment list, you cannot get the structure for disorder regions. So we want to say this should be the same for the predictor. So this is what we did. For a sequence, we predict disorder region, we remove them, and we denote this by sequence plan. So this is one special treating. Another one is this is still geometry prediction, but we did this very simple. Jianyi already introduced using template and AF312. And from this MSA, so we use this information in the predicted order. We cut this MSA with a new resulting in a new MSA plan, and this new sequence and the new MSA will be inputted to AlphaFold2 or our own method TLZX2 to predict the structure. And for AlphaFold3 is only a solver. We don't have much choice. We just input the new sequence, and this is still geometry information to AlphaFold3 server to predict structure. So we have three different predictors here to predict the decoy for the input sequence. But for our own method, TLX2 is only used for monomer prediction. And AlphaFold2 and AlphaFold3 can be used for both monomer structure and multimer structure prediction. So from this predicted decoys, we use QA method to select the model to submit. And we have three groups here. You can see the previous steps are the same, but the major difference is in this QA stage. We use different approach to select the models. And for this home group, we manually verify the model, but sometimes it's not working because we are not very knowledgeable about the structure. So this is the overall overall pipeline we did in CASP-16 for our groups. Okay, next please. Yeah, this is the MSA generation. This pipeline is largely the same as we used in last CASP-15. So here is, but I want to say one difference is here because we predicted the disorder region and remove the disorder region from the sequence, and now the difference is when we generate this multiple sequence alignment, we are using the new sequence, not the original one. No, use the original one and then cut this MSA by the disorder region. So that's the difference from last CASP-15. And then from this, we have multiple set of MSA and just use this TLZX2 to select the optimal one because it's very fast. We can do the selection quickly. We don't need the structure. Yeah. And okay, this for something wrong. So this is the one I talked about. So from this sequence, the first step we use the disorder tree to predict disorder regions. Then you get, for example, the red one are predicted disorder region, and this will be removed when you go to the structure prediction. This is one thing we did. And for this optimization, we also use this predicted disorder region to cut this. For this example, we have the head and the tail, N terminal and C terminal cut out before we go to the structure prediction. Okay. Yeah, next please. Yeah, this is a monomer structure prediction. We get this new sequence and a new MSA, and we just get these three methods to predict the structure model and use the QA to select some by models. But I want to say that for this multimeric targets, we have the monomer targets, and we just use the structure from multimeric modeling to deduce the monomer models, unless the multimeric structure model is in low confidence. And for the multimer structural prediction, so I think it's essentially the same as the monomer. So we just for each chain, we cut the disorder region out. And for alpha-fold multimer, we just build the optimal SA and the monomer pipeline. And for the alpha-fold 3, because it only accepts the sequence. So they will just input the new sequence to the server, and we collect the predictions. Yeah, then we do the clustering and QA and select the top-5 model to submit. So let's go to the results. So you already see this in the official website. So I just get this screenshot yesterday. So you can see for this monomer prediction, our 3 groups are at the top 3. And for this monomer multimer prediction, if you rank by this larger than 0, so we are at the 3rd. And if we rank by this larger than -2, then we can be the 2nd. So this is the overall ranking. So I will go to some examples to show what we did, how we optimize the sequence here. So here we have 5 examples. So they are all multimers. So I will go to the first one. So this is a very large target. So this is a protein RNA protein RNA complex. So you can see this one is a native structure, and this is one what we submitted for this hybrid one. I'm not sure probably we remove the RNA for the submission, but in our model we have this RNA, and you can see to compare with AlphaFold's default model, you can see this is submitted Epsilon's groups. So group 304. So you can see this default AlphaFold 3 model is different from this one. You can see by intuitively their shape is similar. So I will show you how we did this. Yeah, for this one is what I said in my title. We optimize the sequence. So this is important. Why? For this target, they contain about 6,000 tokens. It's larger than 5,000. This is the limit of AlphaFold solver. So then you need to remove this disorder region. This is also the real situation for the experimentalist to solve structure. So you cannot get his disorder regions. So we put disorder region for all chains. And for this 6 chains, we remove out the disorder regions. So by doing this, so you can significantly reduce the number of tokens to about 3,700. And if you take a look at this native structure, it's about 3,000. So these 2 numbers match very well. So this gives us a chance to predict structure with AlphaFold solver, AlphaFold 3 solver, and polymerase this shape overall is almost the same. Although it's not completely accurate, but it's still much better than the default one. Yeah, so this probably this is kind of boring. I show you probably the S1 to S8, the matching of the structure. And say for the first subunit, it's located here. This is native, and this is our prediction. You can see the location is correct. And this the model matching, you see, its statistical score is about 70%. So this rating are very hard to predict, but the overall shape is correct. Yeah, I will go through this quickly. This is S2, probably move on. So S3, S4, S5, S6. Yeah, probably this we have two copies of this subunit. So also our prediction is correct. So this is one, this is another. It's matched very well. Okay, the S7 and for the another one, the last one. Yeah, so this is another subunit in the evaluation. So this one you can also see it's matched very well, and especially this domain. If you predict it isolated as a monomer, then you cannot make it very well. So this is what we did for this special target. Okay, so let's move to the next target. This is a filament. This is very in fact at the beginning it's just released a monomer, but later it's re-released as a filament. You see, for this one we find multiple templates in PDB. This is one of the one we take a closer look. This is the PDB ID colored by different chains. You can see this is very big. So for this chain, it spread from this side to this side. So we use this as a template later for superposing. Yeah. So let's take a closer look at this target. So when you submit this target to AlphaFold 3, you will get this model. So this is color from N terminal to similar. And of course, we remove this disorder rating at the C terminal. So we just submit this rating, and you get a model with ranking score of 81. So the problem is, this rating is perfect. The problem is with this rating from between this 688 to 722, 726 rating. And you can see this part, this is the confidence score. The red one means high confidence, blue means low confidence. You can see this rating has very low confidence. So you see why this is happening, then we go ahead to check AlphaFold 2 prediction. So it's similar for AlphaFold 2. This model, the confidence is higher, it's fairly similar. It's again the issue with this rating. So the confidence is very low. Now we are wondering why other rating are correctly predicted but not less rating for both AlphaFold 3 and AlphaFold 2. Okay, then we just check the template. So this is one of the template from HH plates. You can see this template, this rating. This is I think this is PDB-ID. You see this is A70. That's this point. So it means you compare this query sequence to a template. There is insertion of this or deletion of this region in the query sequence. So this gives a hint. We can probably improve the prediction by insert this sequence from a template. So that's what we did. Yeah, so this solution, we just insert this segment to this position and make a new sequence and submit it to AlphaFold 2 or AlphaFold 3. Yeah, so this is what happened. So when we submitted this new sequence to AlphaFold 3 server, the same for AlphaFold 2, you can see this significantly improved from this confidence score from 1981 to about 19. So especially if you look at this region, you can see the model gets improved significantly. And this blue rating this maps to the inserted segment. So it does not matter whether it's good or not. But this rating it becomes better than before. Okay, sorry. Yeah, so we have 3 domains for this target. Okay, this is for 3 domains. Then you can just separate these domains and use this template to suppose. Then you get it correct. Okay, let's go on. Okay, I will skip this one. It's just a domain assignment. And this another one is big one. So if you use AlphaFold 3, then it's bad. Especially if Jianyi already showed this one. So you can probably go ahead. Yeah, this is what we did. We just split this target into segments because we think the low confidence is because the wrong convolution between the N terminal and the C terminal. You want to avoid this. You will just cut them into 3 segments with overlap and suppose them, then you get this correct model. Okay. So this one probably is what we did wrong. We removed this order region, but unfortunately, this region is binding interface, so we cannot get it correct. Yeah, keep going. Previous one. Next one. Yeah, this one you feel in the phase 1 and 2, we find this problem. Then we just predict the interface between this chain B, C, and chain A. Then you will get the model very perfectly. Okay, last one. So this is one what we didn't do it correctly. We get a wrong stereochemistry prediction. If you get this correct one, yeah, it will be work. Okay. Yeah, so finally is my conclusion. Yes, this one. So what we said is important. You need to optimize the sequence. That is all rating need to be removed out. This is to make it possible to use AlphaFold 3 and also make the prediction better. And also this stereochemistry is important. And for this CASP-16, we think that for our method, MAC optimization is less important than before. And also we see that AlphaFold 3 is better than AlphaFold